Okay, today we are going to be finding a generalized factorial function. So pretty much what that means is we need to find a way to define the factorial function that works for anything except non-zero integers, or non-zero positive integers, pretty much. This is the factorial function for integers. It's the product of all integers less than n, starting at 1, going all the way up to n. So 3 factorial equals 3 times 2 times 1. 4 factorial equals 4 times 3 times 2 times 1, etc. We also know about this is that n minus 1 factorial is equal to n factorial over n. So 0 factorial is going to be equal to, that's 1 minus 1 factorial is going to equal 1 factorial over 1, which is 1. So this is defined for positive integers, 0. What about negative integers? Well, if we try negative 1 factorial, we're going to get, well, negative 0 minus, negative 1 is 0 minus 1. So it's going to be 0 factorial over 0. And you can see the problem here. So this is undefined, but it is an asymptote. So positive and negative infinity. If you did this in the limit, if you took the limit of 0 factorial or 1 over 0, you can approach from either direction and you will get either positive or negative infinity. And you can see if we do this for negative 2, you're just going to be multiplying an undefined number by another undefined number, so that's not great. It's undefined, but it is, there is a way to quantify it, I guess. It is essentially infinite. So the first thing we're going to do here to figure this out is take a look at the derivative, specifically the nth derivative of x to the n. Alright, so what you'll notice here is that this satisfies our definition, right? If we plug in, let's say 4, if we plug in 4 here, let's just do this. We're going to get 4x cubed, 12x squared, 24x, and 24, which is indeed 4 times 3 times 2 times 1. So this works, right? We know that d to the n, dx to the n, nth derivative of x to the n equals n factorial. But we can, what you'll notice is this is just a number, right? So if we say, took something like this, right, we take the nth derivative, x to the n, plus the n minus 1 derivative, and we just kind of continue that on. Second derivative, x to the n, the first derivative, x to the n. All of these have an x. All these have an x. So they're going to equal 0 at x equals 0. So here's where we're going to find our first trick, I guess, or first step turning this into something useful is if we can turn this somehow into an integral such that it's defined in terms of a function that we do know, then we can, even if we don't know the exact value of, like, let's say 3/4 factorial, we can numerically approximate it using a numerical integrator. So let's turn this into an integral. We know that we need to have it evaluated at 0. So I'll set 0 as the lower bound here. But if we evaluated anything else first of all, these x's are going to lead to another result. So we need to add an f of x inside and set our upper bound to a. And what we essentially need is that f of x times this polynomial, because this is a polynomial, equals 0 at a for all n. One way to do this was just to be set a equals infinity, right? So it's going from 0 to infinity, and we need f of x such that f of x it overpowers this polynomial, right? It shrinks to 0 faster than this polynomial shrinks to infinity. And one thing that we do know is that exponential functions do faster than any degree of polynomial. So that's what we're going to do. We're going to set f of x equals e to the negative x. So it's going to be 0 at infinity, but then we're going to have to subtract this, right? This is going to be 1 when x is equal to 0, so this holds true, and this is going to indeed be n factorial, right? Because you're isolating for this term right here. But we're subtracting that from our 0, so this actually needs to be negative e to the negative x. So now we have something that we can turn into an integral. Negative e to the negative x times the summation of all the nth degree derivatives of x to the n, right? Right, this is now what we have, and we're evaluating that at 0 to infinity. Now we know that this is going to be the antiderivative of our function, right? If we're integrating this from 0 to infinity, g of x, this is going to be capital G of x, such that dg dx equals g of x. Right. So one way to figure this out would just be to differentiate this. We now need to differentiate this. Negative e to the negative x times this polynomial. So let's do that. Let's find d dx, negative e to the negative x, and then I'll just write in I'll just write in 4 terms here. All right, nth derivative x to the n minus 1 derivative x to the n, and then first derivative x to the n after, and in between this is just the rest of them, right? So the product rule says that this is just going to be the derivative of this times this plus this times the derivative of that. So we're going to, that this negative comes down, we just get e to the negative x times this and then it's going to be plus negative e to the negative x, and then this is, you just need to differentiate this. So it's going to be d to the n minus n plus 1 over dx to the n plus 1, x to the n, plus d to the n dx to the n, and then the second derivative, x to the n. And what you'll notice is that, first of all, this term, right, if we remember, d to the n dx to the n is just n factorial, which is a constant with respect to x. The derivative of a constant is just 0. So this term's going to cancel out. And we're left with this, right? This negative here, we can just factor this out, right? And you'll see that we have some repetition here, right? We get this, and we can take that out, right? You're going to have this n minus 1 in there. You're going to have the second derivative in there. So everything cancels out. And we're left with g of x equals e to the negative x times the first derivative of x to the n, which is just nx to the n minus 1. So let's just continue this on another page. So we know that g of x equals e to the negative x nx to the n minus 1, and we need to find the integral from 0 to infinity of g of x dx, and this is just going to be, we'll just factor out the constant for now, e to the negative x to the n minus 1 dx. That is quite nice, because that is something that we can actually evaluate, and we can solve numerically for some non-integer values of n, and this is equal to n factorial. What we'll notice is that we can divide both sides by this n. All right, we'll just cancel that out. Divide by n over here, and this, going by our definition on the first page, is just n minus 1 factorial. Right, this is our solution, and this is it. The integral from 0 to infinity, e to the negative x to the n minus 1 dx is equal to n minus 1 factorial. And what you'll see is that we can just add 1 to both these inputs, and we find that n factorial is equal to the integral from 0 to infinity, e to the negative x to the n dx. Thank you.